Trees, the silent giants that have existed for hundreds of millions of years, have honed their design to perfection through the trials of evolution. It is within this dynamic struggle of existence that the nature has crafted a masterpiece of geometric and material optimization. Every single curve, angle, branch placement, etc. serves a unique purpose, optimally transferring the load, capturing sunlight, and transporting nutrients and water effectively. Today, we explore the remarkable design of these beautiful organisms. Let us start by simplifying the structure of tree in order to better understand the load transferring mechanism. This process is called as idealization. The weight of the branches transfers to the trunk, which serves as the main support system. The trunk carries most of the tree's mass and in turn transfers the load to the root. The roots provide anchorage and they act as the fixed support to prevent vertical and horizontal motion as well as rotation at tree's base. If we were to examine tree from the top, we would realize something interesting. Firstly, tree tries to grow symmetrically about all three axes. And secondly, if you move from top to bottom in the downward direction and consider small differential elements such as thin discs, you would realize that the mass they represent increases progressively as you go down. This variation suggests something important. That is, the uppermost reaches of tree, or its ultimate top, can be conceptualized by a mere point. On the other hand, the lower reaches represents higher mass. This indicates accumulation of mass as you go from top to the bottom of tree. This idealized geometry of tree, like any slender structure, can be considered as a configuration in three-dimensional space which can be defined by means of locus of geometric centroid called as midcurve and the family of cross sections that are attached to this midcurve. Four important questions arise in regard to tree's structural design. Firstly, why does the area of cross section of the trunk or the branch increase as we go from top to the bottom of tree? Secondly, what is the secret behind the cross section of the trunk or the branch being almost circular in nature? Thirdly, why does a tree strive to maintain a straight profile? And fourthly, what if a tree fails to maintain symmetry? How does it adapt to rotational loads, that is moment, introduced as a result of eccentric growth? Exploring each of these rather simple questions holds the key to understanding the ingenuity in the structural design of the tree. To answer these questions, we start by noting that analyzing any structure or its design consists of three components. The first is to understand the loads acting on the structure. The second is to understand the material that the structure is made up of. And the third is to understand the geometry of the structure. The external forces acting on the structure induces stress in the material that leads to deformation. The material not only have to be strong enough to resist these stresses, but also optimally configured geometrically to withstand these stresses effectively. One of the major forces that a tree has to withstand is its own self-weight. And this force varies along tree's height. At the pinnacle, it is minimal or zero, and it gradually increases as we descend from the top to the bottom of the tree. As a consequence of this, the lowest cross-section of the trunk experiences the greatest amount of compressive forces. To counter these compressive forces, the cross-section of the trunk or the branches gradually increase as we go from top to the bottom of the tree. This smooth change in the cross-sectional area of the trunk or the branches also reduces the stress concentration. Over time, as tree grows taller and heavier, its trunk undergoes a gradual increase in cross-section by adding growth rings. This addition of growth rings not only helps in resistance of structural loads, but also assists in biological operations that become more and more complex over time. By continuously augmenting the cross-sectional area in both space and time, a tree optimizes its ability to withstand gravitational load, all the while performing all the necessary functions that are necessary for its survival. Self-weight is not the only force that trees face. Relentless winds that sweeps through their branches imparts lateral loads, that is, forces acting from the side, and this causes trees to bend. As a result of these lateral forces, a portion of tree experiences elongation and is subjected to tensile stresses. On the other hand, other portion of tree experiences contraction and is subjected to compressive stresses. This is a typical stress profile of a slender structure subjected to bending. Varying speed of winds in horizontal plane also induces torsional deformation in the tree, that is, rotation about its own vertical axis. However, bending is the most dominant rotational effect that a tree is subjected to. To comprehend the wind load, let us consider a situation where wind is blowing in one direction from left to right, that is, in the x direction. And we also assume a random wind profile where the velocity of wind varies as we go from top of the tree to its bottom. Such a wind profile will lead the tree to bend from left to right about an axis which is perpendicular to the direction of wind. Let us call it y-axis. As we move from tree's apex to its base, every single cross-section experiences a rotational effect, that is, bending moment. At the uppermost reaches of tree, the bending moment is minimal. However, it progressively intensifies as we go from top to the base of the tree. Another effect of wind load is to introduce shear stresses in tree. That is, because of the lateral load, trees tend to shear, and the intensity of shear forces increase as we go from top towards the base of the tree. This prompts a thought-provoking question. What geometric property of cross-section enables it to resist bending? For example, if you consider a ruler, it bends easily about an axis that has lower moment of inertia. However, if you attempt to bend it about an axis that has larger moment of inertia, it becomes much difficult to do so. Since bending moment increases as we go from top of the tree towards its bottom, a tree strives to possess a cross-section that has higher moment of inertia at the bottom relative to the top. For a circular cross-section, the moment of inertia about any axis is directly proportional to the fourth power of diameter, and therefore an increased cross-section at the bottom of the tree significantly enhances its capacity to withstand bending moment that is imposed on it. The increase in the area of cross-section of the tree as we go from top towards its bottom not only effectively helps in resisting wind loads, they also lower the center of mass of the tree towards its base. This helps reduce the likelihood of tree overturning under wind loads. And finally, the roots provide enough anchorage or fixed support that can resist overturning moments. Trees also have to deal with unpredictability in the direction of wind load, and this makes the axis about which a tree bends unknown. To address this variable loading scenario, trees have evolved a remarkable solution, having an almost circular cross-section of the trunk and the branches. Due to its symmetry, a circle is the only cross-section that have the same moment of inertia about any axis that passes through its centroid in the horizontal plane. This characteristic of a circular cross-section enables a tree to resist a laterally acting forces such as wind load or earthquake load acting in any direction. Trees also possess a degree of flexibility that allows them to sway in the direction of wind or bear seasonal loads such as snow. This flexibility helps dissipation of energy of external forces and reduce the risk of failure. Additionally, the damping property of wood allows it to dampen the effect of vibrations due to dynamic loads such as wind or earthquake. Now, let's talk about overall symmetric shape of tree. It's often the case in many trees to have spread out branches to help with transpiration, breathing, photosynthesis, and other biological processes. The spread out branches provide higher surface area for the exposure to sun, aiding in the process of photosynthesis. The growth of the tree and spread out branches mostly occur symmetrically, and this reduces eccentric growth and provides straight profile to the tree. The branching of tree often follows a self-similar pattern called as fractal branching, where same pattern of branching repeats itself at different scales, and this helps in distribution of the loads more effectively. When a tree grows on an inclined plane, it tends to straighten itself up through tropisms, that is, by growing towards the sun, and this reduces the total overturning moment that the roots have to resist. It is observed that the root of the tree grows in the direction opposite to the inclination of the tree, and this provides proper anchorage to the tree by facilitating required resisting moment at the bottom of the tree and thereby preventing the tree from overturning as a result of eccentric growth. The fibers running along the trunk and the branches serve two purposes. The first is the transportation of water and nutrition, and the second is to provide structural reinforcement to the tree. The continuous extension of the fibers from the stem to the branches provide nearly fixed support at the joint. Any structure that is subjected to bending experiences axial stresses across its cross-section. A portion of the cross-section is subjected to tensile stresses, and the other portion of the cross-section is subjected to compressive stresses, that is, pull and push stresses respectively. These fibers are aligned in the direction of these stresses, and therefore they provide appropriate reinforcement to the tree so that the tree can bear these stresses more effectively. A tree is exposed to complex and extreme loads, some of which includes its own self-weight, wind load, snow load, and earthquake load. The material composition of each tree differs from its location, terrain, soil quality, sunlight exposure, rainfall, and many other factors. And this is precisely why each tree has a uniquely tailored geometric and material composition that suits its own needs. Wood has evolved over time, being subjected to different environmental conditions. Wood is a highly composite and complex material that is organic, highly anisotropic, inhomogeneous, and tailored to each tree. The adaptive design of tree does not stop there. Trees have an ability to produce reaction wood in response to mechanical stresses. There are two types of reaction woods. The first is the tension wood that is usually formed on the upper side of the branch or the leaning system, which are subjected to tensile stresses. On the other hand, there is compression wood, which is usually formed on the lower end of the branch, which is subjected to compressive stresses. These specialized wood types help trees adjust their growth patterns and effectively counter gravitational forces acting on them. When a tree is subjected to damage or infection, it has an ability to compartmentalize the affected areas, forming barriers which prevents further spread of decay or disease. Finally, trees exhibit tropisms, that is, growth responses to external stimuli. Phototropism allows the tree to grow towards the source of light, aiding in the process of photosynthesis. On the other hand, geotropism allows roots to grow downward in the direction opposite to that of gravity. By now, you've seen how beautiful the structure of tree is and how well designed it is. We saw how the tapering cross-section of the tree from top to bottom helps resist self-weight in a very effective way and minimizes the risk of overturning. We saw how the circular cross-section of the trunk and branches help resist bending moment due to unpredictable winds. And most importantly, the adaptive strategies such as growth rings, reaction wood, and tropisms help tree adapt to environmental conditions and maintain structural integrity over time. I hope you enjoyed the video. If you like the content of the video, please give me thumbs up and subscribe to my channel for more upcoming content like this. Until we meet again, more power to you.